Extreme drought events have now been linked to both tree mortality and losses in forest productivity on every forested continent on Earth. As we expect the scale of this problem to amplify as global climate change causes increases in the intensity, duration and frequency of extreme drought events, research that looks at how and why forests respond to these events is becoming increasingly important. Our research is trying to understand how resilient Scots pine trees are to extreme drought and how they recover. Scots pine is excellent for biodiversity and is widely grown for its timber, making it both an ecologically and economically important species. Scots pine is actually one of the most widely distributed conifer species in the world. Its core native range is highlighted here in light green and stretches across much of Europe. Its current distribution is even wider as a result of it being introduced or naturalised, which are the dark green areas, and occasionally found even further afield in isolated pockets. Our study site is an experimental forest of Scots pine trees that was originally planted in 1935 by Forest Research in the north of Scotland in a place called the Black Isle, just north of Inverness. And it was these trees in this experimental forest that we used to answer our research questions. First of all, we wanted to understand how resilient these trees were to an extreme drought that occurred at this site in 1984, and we can think of resilience as the capacity to bounce back. Secondly, we wanted to understand how long they took to recover, and thirdly, we wanted to understand what happened to the growth of these trees after they'd recovered. To do this, we used tree rings collected from these experimental trees. We can think of tree rings as being a bit like fingerprints, where the lines of a fingerprint are unique to every person. Each tree ring holds the record of that tree's unique relationship with climate and other variables every single year. As tree growth is tightly coupled to how favourable a given year's climate is, generally speaking, where we find wide rings, we also find that the climate in that same year was good for tree growth. In contrast, narrow rings often indicate that climate wasn't very good for tree growth, like in a drought year where it was too hot or there wasn't enough water. By taking tree cores or cutting cross-sectional discs from tree trunks, we can actually measure the width of each individual year's tree ring. We can then use the width of narrow rings that we know were formed from climate records during a drought year to give us an indication of how much of an impact that drought had on tree growth. The idea behind our study was to use tree rings to calculate the annual growth rate of each tree, represented here by the white line, before, during and after an extreme drought event. Next, we captured the relationship between annual tree growth and climate up to and including the year before the drought event using a statistical model. Then we could use this relationship in combination with the actual climate data during the post-drought period to forecast annual tree growth in a scenario where no drought had occurred, represented here by the pink line. This would allow us to calculate the recovery year, i.e. when growth returned to normal, and develop an understanding of how individual trees recover from drought throughout the recovery period. However, what remained a real unknown was how well these trees would continue to grow after they had recovered, and we were interested to know if they would underperform, overperform, or continue to grow as forecasted under a no-drought scenario. We found individual trees, represented here by the coloured lines, were highly variable in how resilient they were, with each dot indicating the year in which a tree recovered. Similarly, we discovered that trees growing faster before the drought bounced back quickly, while larger trees bounced back more slowly. By comparing how fast the trees grew during and after the 1984 drought with how fast they might have grown if no drought had occurred, we calculated both the annual and cumulative growth deficit for each tree, represented here by the white lines. We then used this information to calculate the total impact of drought on tree growth for all trees collectively every year, as well as the cumulative impact over time. On average, tree growth took about 4 years to recover to levels we might have expected if no drought had occurred. The green area indicates the growth deficit for all trees combined for every year of this 4-year recovery period. We could then add up this annual deficit over these 4 years to estimate the cumulative impact of tree growth caused by drought, indicated by the purple area. But this was only half the story. After they'd recovered, some trees' growth exploded, going into overdrive and growing faster than we would have expected if no drought had occurred, acting to compensate for some of the previously lost growth. The net effect of this compensatory growth was powerful enough to allow the forest to recover some of its lost biomass and reduce the cumulative deficit. As a result, the impact of the 1984 drought on forest growth was less after 9 years than it was after 4 years, indicating that short-term assessments of drought impact could underestimate forest resilience and overestimate drought impact. There are a couple of possible non-mutually exclusive explanations as to what might be happening here. Our results indicated that slower growing or larger trees were disproportionately affected by the drought event. The disproportionate impact may be resulting in a shift in the competitive dominance of individual trees, with some trees benefiting from drought while others lose out. Equally, trees may be shifting how they allocate their valuable carbon resources during and after drought. Instead of putting on radial growth, they may be preferentially allocating carbon to expand and repair their root system to access water, or similarly they may be repairing their canopy to capture more sunlight. The compensatory growth that we see when looking at tree rings collected from the trunk may actually be reflecting the way in which these trees are prioritising the growth of other organs and then subsequently playing catch-up to recover this lost radial growth. Understanding the total impact of extreme drought events on tree growth is important for informing forest management, global carbon budgeting, and understanding how these events feed back to influence climate change. To achieve this, we need to consider longer-term processes such as compensatory growth and develop a more comprehensive understanding of how trees allocate resources under stress. Equally, while our study documents compensatory growth after drought in Scots pine trees growing in Scotland, we now need to see whether this mechanism exists in both other species of conifer and in broadleaves. Similarly, we need to establish if compensatory growth exists in other places, and if so, under what conditions, before we can draw any wider conclusions. This is important as compensatory growth will likely still depend on favourable climate while trees recover, and increases in drought frequency and severity could quickly overwhelm any benefits. While this study was conducted as part of my PhD, like all science, it wouldn't have been possible without an amazing team of people and without the financial support from Stirling University, Forest Research and the Scottish Forestry Trust. To find out more, you can read and access the full study by searching the title or following the link below, or get in touch with me directly if you have any questions.